Good morning, good afternoon, and good evening, everyone. My name is Ranpeng. I am a PhD candidate at GeoMar. And in this presentation, I will be talking about our recent work on modeling how phase transitions affect the mantle convection using an entropy implementation with aspect. There are many open questions about mantle convection. For example, we don't fully understand how the convection pattern changed as Earth evolved. The geochemical data has suggested that there could be some different reservoirs and even primordial components preserved in the lower mantle, which means the Earth is not super well mixed, which can be caused by some layering in the convection, maybe. But the geophysical observations sees that for today, the slab can subduct all the way down to the bottom of the mantle, and that's where plume rise. So this whole mantle convection should be quite efficient. However, we are still not sure if there was any layering in conduction in Earth's past. The phase transition is an important factor that can cause layering and affect convection style. The transition with positive Kelvin slope would occur at higher pressures when the temperature is higher, which means if we have a plume, inside the plume, it will be less dense than the surrounding mantle. This positive buoyancy can further accelerate the plume. And for the phase transition with negative Kelvin slope, the effect is the opposite. Inside the plume, it will be denser than the surrounding. This negative buoyancy effect can hinder the plume from upwelling and potentially induce layering. So now let's take a look at what phase transition exists in the mantle. So here we are looking at the thermal expansivity of a perlite compositions plot over a temperature and pressure range. So these dark blue and red colors are where phase transition occurs. The blue ones are transition with positive Kelvin slope. For example, this one is 410, and the red are those with negative slope. And by the way, 660 is here, and it's super sharp to see. And I would like to draw your attention to this phase transition here. That's the transition from UCI to meteorite garnet plus ferropericlase. This transition has negative Kelvin slope, so it can potentially impede and mantle flow and cause layering. And as we are plotting the different mantle adiabats on this diagram, we can see that this phase transition would only exist in the mantle that is hotter than today's Earth, like 1800, 1900 Kelvin. And as Earth cools over time from a higher adiabat to a lower one, it's moving away from this phase transition, and this can maybe cause a change in the convection style. So to better resolve the phase transition, we apply a recently developed entropy method, which is described in detail in this paper, if you are interested. Most importantly, we reformulate the energy equations from pressure, temperature space to pressure and entropy space. In this way, we can fully capture the thermodynamic effect of the phase transition. We also use a material property lookup table to fully and naturally include the complex phase relations through their change in physical properties. So just briefly going through the model setup. We run 2D analysis setup, like seen here, and we set entropy as one of the compositional fields. To do this, it is required to use the entropy assemblers in aspect, which can be found under this path. And the only thing we prescribed is the core mantle boundary and surface entropy. We use a reference viscosity profile from Steinberger and Calder-Wood, which is shown here. And for our models with higher starting temperatures, we make this profile less viscous. we have plastic deformations in the models, which help us to form plate-like subduction, as shown here. We choose a homogeneous parallel composition, and the lookup table is calculated by the code Hephaestus. So now let's moving on to the results. So we will be looking at 3 different quasi-steady state models that each has a different starting mantle potential temperatures. So they can represent Earth at different stage of its cooling. So the first one, the current one, has a starting adiabat of 1600 kelvins. So it can represent today's Earth. And the color are just temperatures, and these lines are just some temperature contour. And these blue are the subducted fossil slab in the lower mantle. And here we can see the plumes can rise all the way straight up to the bottom of the lithosphere. And now for the second model, the starting mantle potential temperatures is 1700 Kelvin. So it's like going back in time for Earth. Now we can see the plume is slightly tilted at around 500 kilometer depth by the phase transition we just discussed. And now let's further increase the mantle potential temperature to 1800 kelvins. So we are in an even earlier stage for Earth. Now, very obviously, these plumes conduits are strongly tilted and layered at around 500 kilometer depth by the phase transition. So the layering of the plume we just saw in those snapshots can also affect Earth's long-term and large-scale thermal structure, which can be seen in this plot. So we are looking at how the averaged entropy at each depth changed with the model evolution time. So the y-axis is the depth and the x-axis is the model evolution time, which means that each column of these plots represents the whole models at a certain point of the time. So these blue are some cold subducted slab accumulating in the mantle, and these red stuff are hot plume materials. So now if we compare the 1600 Kelvin, 1700 Kelvin, and 1800 Kelvin models, we see separate hot temperature layers exist right below 500 kilometer depths, existing only in the 1800 Kelvin models, and that is caused by the layering of the plume at the phase transition. So we just look at the quasi-steady state models that each represent a certain time during Earth's evolution. We also have a long-term models that run for 3 billion years and can show the gradual change from a hot mantle cooling down to a cold mantle, and that's what we are looking at right now. So this model started from a 1900 Kelvin mantle potential temperatures and cools around 100 Kelvin per billion years. And now we are still at a quite early stage. And if I pause, we can see these plumes are strongly impeded at around 500 kilometers by the phase transitions. And I will just jump within time. And now everything is more blue, so the mantle is cooling down mostly by the frequent subductions. And now more and more plume can rise straight up. And if I go to even a later stage, now almost all plume can rise straight up and without being strongly affected by the phase transition. So this gradual change can also be seen if we look at the vertical velocity of plume. And that's what we are plotting on this diagram. That is the vertical velocity variations of plume change versus model runtime. So basically the red color means the plumes are accelerating and blue means they are decelerating. And we can see a really obvious and strong decelerations of plume for the first at least 1.5 billion years of the long-term model. And then the decelerations become weaker and weaker, and it's eventually gone for the later stage of the model. So based on our results, we can draw regimes for the layering and non-layering. So here on this regime diagram, every circle represents either a quasi-steady state model or a 300 million years time interval of the long-term model. And the x-axis is the starting Mantle potential temperature. The size of the circles is the degree of the layering, which is quantified by how much the vertical mass flux are reduced by the layering. So for the models with a Mantle potential temperature hotter than 1750 Kelvin, they are in layer regime. The hotter the Mantle is, the stronger the layering are. And for our hottest model that has a 1900 Kelvin potential temperatures, the layering can reduce the mass exchange between lower and upper Mantle by about 8%, which means it's a strong effect, but it's not strong enough to cause fully layered convection. I hope it doesn't disappoint you. And for the models cooler than 1675 Kelvin, they are in non-layer regime. And in between the layering and non-layering, there is a transition regime where we can still see the tilted plume and layering of the plume, but they are not strong enough to cause a global mass flux reduction. And with this regime, we also want to show that from layering to non-layering, we don't see a sudden overturn. We see more like a gradual change with time. And our global convection models are all in 2Ds, but I just want to mention that we see a very similar effect in 3D models. So these are some simple 3D box setup with a plume rising. The top panel has a potential temperature of 1600 Kelvin, and the bottom one has a Mantle potential temperature of 1800 Kelvin. And we can see very consistent with the 2D observations. The plume are strongly tilted and layered only at the phase transition, only in the hot Mantle. So this layering of the plume have very interesting implications for Earth's evolutions. First, obviously, it can make the transition zone much hotter because of all those trapped hot material. And also, as Earth is transitioning from layering to non-layering regime, we observe an increase in surface mobility. Also, the plumes, there can be a lot of secondary plumes generated from the layering. And if a plume head is trapped, it can cross the solidus and form some partial melts. And as it's spread out and a secondary plume rise from the different locations, this process can potentially geochemically differentiate the plume. And here you can find our various plume morphologies in this schematic summary diagram, and also the different regimes and the time it could corresponding to. And this time period of the regime are calculated assuming a cooling rate of 100 Kelvin per billion years. And the most important takeaway is that the OCI to garnet plus clays transitions could induce layering, could hinder plumes and induce layering when the Mantle was hotter, like in Earth's past. This layering is strong, but not strong enough to cause fully layered convection. And you can find all of the details about this study in this paper, which is just published a few days ago. And we are currently working on expanding the entropy method to incorporate multiple components. And if you have more questions, you can find my email there. Thank you.
All right, thank you very much. Great talk. If you have any questions, please write them down because we'll be now moving on to the next talk by Alan Yu. So if you can start sharing your screen. The title is A Recipe for Exotic Continental Fragment Formation, Automated Data Analysis of Rift Models.
Can everyone hear me?
Yes, I can hear you.
Okay. Can you see the screen as well?
I can see, yes.
Is there a presentation? Okay,
Yeah, it looks
lovely,
good.
lovely. Thank you, Mantle. I hope Graz is fun for you now. It's getting quite cold here in Potsdam. Hello, everyone. My name is Alan. I am a PhD student at the GFZ. I'm working with Sasha Brunet and Judith Bott now. But for this talk, I am fully Team University of Toronto. I'm presenting my master's thesis that I did with both Erkant, Kent, under the supervision of Professor Phil Heron at the University of Toronto. So I'll start this presentation with a very beautiful map. It's called the Hazen-Thorpe map. It was produced by American geophysicist Murray Thorpe in the 1950s, following a series of submarine surveys. Her map unveiled a new list of features that we didn't see previously, and that is set to revolutionize how we see the Earth. So from her map, we can see subductions, notably the Pacific Ring of Fire, as well as mid-ocean ridges, notably the Mid-Atlantic Ridge. Tuzo Wilson, from the University of Toronto, string these features together into an ever-evolving Wilson cycle that is set to govern the Earth since plate differentiation. However, as we zoom in, we see that the general view of the Wilson cycle, though widely accepted, does not explain more nuanced tectonic scenarios. About 60 million years ago, the Labrador Sea opened between Canada and Greenland. And what's interesting here is that the opening of this seed separated a piece of Greenland here, named the Name Province in eastern Canada, away from Greenland. This is what we define here as a continental fragment, which is a small piece of the continent that was separated from its parent tectonic plate. We know that because they share the same geological signature and history prior to the separation. As we look throughout the entire globe, we realize that the separations or the opening of North Atlantic, South Atlantic, and Indian Ocean has created a number of these geological examples. And an emerging question to the geologist and geophysicist is how they were formed. Here, we propose that structural inheritance from previous old Wilson cycles can promote the formation of continental fragments. At convergent boundaries, we have subduction. Subduction can create profound deformation in the overriding continental lithosphere through melting, plate shortening, volcanism, and sometimes even backyard rifting. The consequent continental collision can also produce long-lasting lithospheric scale deformation preserved within the continental lithosphere across both plate margins. These deformations can reactivate and guide subsequent deformation development during extension. And as such, in some cases, we can create a continental fragment. And here we want to use aspect models to investigate if this is a plausible theory. We create 2D models that are 600 kilometers wide, and can you guys see my mouse, or I have to explain it? Okay, 600 kilometers wide and 600 kilometers in depth as well. It features 20 kilometers of upper crust, 20 kilometers of lower crust, 80 kilometers of mantle lithosphere, and the rest being asthenosphere. Each is comprised of a different material with different rheology. To simulate subduction left by the previous subduction, we scale the viscosity, or here we represent as the rheological weakness that's left by the previous subduction within the upper plate margin by this factor F. This factor is simply the ratio of the viscosity of the upper plate margin compared to the lower plate margin. To simulate orthogenic deformation from the previous Wilson cycles, we prescribe a zone of randomly distributed initial plastic strain. And this is the starting stage of our models, in which then we extend the lithosphere from the side and we add inflow from the bottom to compensate for the loss of mass. And this is what we're trying to model here. So I'll explain this movie a bit for the newcomers of Aspect. This is a viscosity plot showing only the top 200 kilometers of the continental lithosphere. So this part is the continental lithosphere, and whatever below is asthenosphere. We have an outline that's tracing the upper crust of the upper plate margin. We can see in a second that from which there will create a continental fragment from here. So as you can see here, a fragment here is being created. And I will do a brief overview of the rift model. So in stage 1, we can see the widespread faulting and strain that's distributed throughout both the entire lithosphere, essentially. And then in stage 2, we can see that these distributed strains start to localize within a well-defined rift locus. This is the stage where we call it as strain localization. And in stage 3, we can see that the lithosphere is being substantially thinned, and we can see a narrow branch of asthenospheric upwelling developed along this rift locus. And eventually, the continent will break, and then you can see that there are 2 new tectonic plates being formed, with this gray line being the previous plate boundary. And here we created a continental fragment in widths of about 260 kilometers. So from the reference model, we systematically tested 8 different physical parameters. This resulted in a total of 94 models and over 5,000 output files. To sort through and analyze all these output files, we implemented an automated system using both ParaView and Python. This system can detect the time of continental breakup. In this case, we define as when the asthenospheric rocks ascends to the surface, and then measures the width of the continental fragment here. So this is a typical model output of Aspect. If you open it with Excel or just a text editor, it would just be a bunch of numbers of different variables. However, with Aspect, we can visualize this output and perform analytical procedures. Here, we want to look at the width of the continental fragment. And the advantage of using ParaView is that whatever you perform can be recorded in Python. And with the power of Python and for loops, we can then automate through all of these output files. And this, in our case, resulted in over 90% reduction in the time of analysis versus measuring it manually while ensuring consistent results. So the first parameter we tested is the dip angle of the O suture. This is defined by the dip angle of the plate boundary that's separating the upper plate margin and the lower plate margin. So here we have 3 different, let me move a window here. We have 3 different models showing dip angles of 15, 35, and then 30 and 45. And then we can play the models here. And all 3 models created continental fragments of different widths. And we can see that the geometry of this dip angle or the inherited structure can control the width of the continental fragment. Between dip angles of 15 to 45, we can see that as you go steeper with the dip angle, you create a smaller fragment. We then run more than just the 3 models, and we evaluated the tectonic influence when we increase the dip angle and when we increase or decrease the strength of the upper plane margin to see their tectonic response. Though between 15 to 45 degrees of dip angle, we can create a smaller fragment as we increase the dip angle. Between 60 degrees of dip and 90 degrees of dip, we can see that there's no clear trend. And also, when we make the upper plane margin extremely weak, we can also see a reverse trend in which if we increase the dip angle, you create a bigger fragment. Next, we modulate the extent of this initially randomly distributed plastic strain to account for uncertainties due to the previous collision and lithospheric orogeny. Here we have 3 different setups with the strain zone being 400 kilometers wide as our reference setup. So these are corresponded to here. There's no movies here, so I won't bore you with more movie. But as you can see, if we increase the extent of the orogeny, we can also create a bigger fragment. And again, as we look throughout all different extents and also different strength of the upper plane margin, we can see that a more extensive orogenic deformation zone creates a larger fragment, with the edge case here being when f is equal to 0.1. Next, we tested the influence of the initial geotherm. Changing the initial geotherm can change the depth in which the brittle deformation and ductile deformation occurs. With a colder geotherm, we can see that the lithosphere is more brittle, and with a hotter lithosphere, we can see that the lithosphere becomes more ductile. So here, I have 3 more movies to show, and I promise that will be the end of it. So we have cold, typical, and hot. So here you can see that the style in which rift occurs changes quite a lot. With a hot lithosphere, you can see that there exist a number of these rift locus competing against each other for strain localization, whereas with a I'll put my annotation here. With a cold lithosphere, you can see that the strain is swiftly localized within a singular locus. And this then can influence our strain localization and hence the fragmentation process. A colder lithosphere here can create a narrow rift, whereas a hotter lithosphere creates a wider rift. In summary, we produce fragments in widths of 175 to about 350 kilometers in width over the time of 15 to 35 million years. We then compare our model results with the previous geological examples, and you can see that many of these examples fall within the range of our model results. And on top of that, they also have a tectonic history with multiple episodes of Wilson cycles governed by subduction, collision, and intraplate deformation. In conclusion, we used an automated system to quantify the influence of structural inheritances in the fragment formation. We found that the geometry of the inherited structure directly controls the width of the separated continental fragment. However, this process can also be influenced by other factors, such as the initial geotherm. Our model results aligned with many geological examples, though in later studies, we would like to look more in depth into regional models, especially creating 3D models. And here we provide a tectonic recipe for future regional models. And that concludes the talk today. I would like to gratefully acknowledge Rene's invitation for me to be in this talk. Aspect is truly an amazing community, and I welcome everyone to participate and contribute. You can also access all the setup, tutorial code, and data by scanning this QR code. Thank you.
All right. Well, thank you for the great presentation. Thank you both for the great presentations, I guess I should say. So I hope that you've all written down your questions, because now there's time for questions. We have about, well, a bit more than 15 minutes for questions. So if there are any questions, please raise your hands, and then I can give you the turn and you can unmute yourself. Renee?
Yeah, hi, Alan. Thanks for the picture at the end, and the talk, of course. I have a question about the script that you mentioned. So how exactly do you extract the plate boundary in that script? Is that some sort of just looking for the weak spot at the surface? Do you use some sort of image recognition? How is the plate boundary defined if the script extracts that?
Good question. Let me pull up the script if I can share the screen again. Here. So with Aspect, you can perform data filtering basically through SQL sequences. Here we defined when the continental breakup occurs, when the composition of the asthenosphere meets the surface, which here we define as the minimum temperature. So then as soon as this criteria is satisfied, then we look into the width of the continental fragment, in which here we defined as the composition of the upper crust from within which the fragment is generated, and where that selection meets the minimum temperature, which is also the surface, and then where that the second selection is met with positive horizontal velocity, in which it means like, because you have a rift, it's symmetrical, and one has to go the other way. So then that's how we define the width of the continental fragment.
Very cool. I've worked with Python power view scripts, but not as sophisticated as this one. This is pretty neat. I think we should advertise this more. Thank you.
Okay. The
Can
next
I
one
add
is John.
something related to that? Sorry.
Okay, sure, go ahead.
Because I'm also trying to implement that script, and actually it's a discussion which comes up quite a lot. So, of course, I do numerical models, but we talk a lot to like observation, like people who do observations. And I'm always not sure what parameters, like for the numerics, of course, it's kind of, you have the fields and Aspect, and you can say, oh, this is Mantle, this is crust. But perhaps like as a general point, what would be the best parameter to actually, for example, define plate boundaries, or say, okay, the features here?
It's a more complicated question. It depends on how you set up your model. Here, because I have a trick in which I prescribe the surface to be always at 273 degrees Kelvin. So then I can use that as kind of like a trick to select the surface. But for detections, there are many, many methods. I've tried when the asthenospheric rock meets a certain temperature, like because when it goes up, the temperature of the upwelling will decrease. It really just depends on how you set it up. If you have a model, I can maybe look at it and then give you some ideas of how we can find or define when the continent breaks up. It's a tricky question.
Yeah, but so like for me, I also need a parameter which is, like an alignment with people who do observations, so that I'm not just like, oh yeah, this is breakup, then nobody believes that it is. Thanks.
Yeah.
Okay, John?
Yeah, I have related follow-up questions to on what Renee asked. So Alan, great presentation and really impressive work. That the workflows you developed are those seem incredibly useful. So I have two questions. Is one, so have you thought about integrating some of these? I mean, so in some sense, they're very similar to some of the ideas in Fatbox, which is for the fault analysis toolkit that Sasha Bruns group has been working on. In general, like the overall structure, not the specific details, but then how do you do automated analysis of models? So then my first question is, have you thought about maybe integrating these tools into a broader, like a broader project in any capacity, or a broader repository?
Is that a question for me? Sorry, I misunderstood.
Yeah.
Oh, okay.
Yes, yeah.
Sorry. Yes, of course, I would like to expand something on like this, because this will be important for my current PhD work, which I need to pick out the faults created by Aspect and then run through fluid flow and heat transfer modeling with another code. So that will be something that I look forward to, but I've thought about it initially too, like how you can pick out the faults and the way that, because all of the first we have to pick a strain rate, and then because of how Aspect handles the material fields, you're basically picking up particles, and then to form from particles to like discrete fault planes is not an easy task, I would say. So I haven't thought of it that far. I'm still running a model to create the faults first, but that is something that I need to consider later. But
Yeah.
But sorry to intervene. I think that's more like my PhD projects, because I need to characterize rifts and determine what's when is breakup and what's the failed rift. So I will probably analyze these parameters.
so sorry,
Yeah.
Tina, you're a DC one, so yeah, I
No, Alan, I should. Sorry to interrupt you.
I'll add
Okay.
one more final point here. Renee, maybe we can bring this up as a discussion point tomorrow. But one issue that comes up, I mean, is that there's all these amazing tools everyone is developing, and it's hard to, and oftentimes there's overlap in the functionality, or oftentimes they could be combined in many ways, and it's often hard to discover them. So this is one of the great outcomes of this meeting, is we learn everyone's doing, but more generally, these sort of model analysis tools it's hard to discover them sometimes if you don't go to the right meeting. So, but there are a number of us who had an idea for a common database, Python focused database, which integrates all these tools. We had a proposal that did not get funded, but we are encouraged to resubmit. So maybe that could be a discussion point for tomorrow, because again, now I see your talk and I think, wow, this is amazing. It would be great if this could be integrated with all these other features. So it's really exciting. But maybe we can discuss this tomorrow during the general discussion.
Thank you.
Yeah, maybe to expand on this. We discussed this before, John, right? This is mostly to let everyone know about it. But so we do have a folder inside of the Aspect repository in contrib/Python, where we already collect some Python scripts to do something with the parameter files or with the output files, whatever you're working on. The problem is that we cannot just randomly merge everything into there, right? We need to make sure that the codes are working and that they are tested, and that there is some sort of example in Aspect how to use them. Otherwise, we accumulate a lot of stuff in that folder that's not really maintained over time. So we welcome every contribution of tools like this, but it always has to be embedded somehow into an Aspect cookbook or benchmark or something. And that's why it would be so great to have a separate collection, like, John, what you were talking about, where the whole purpose of the project is to collect all of these things and bring them into a format that they can be used.
Okay. Yeah, it sounds good for discussion for tomorrow. So Antoinette, next.
Hi everyone, a great talk again to Alan and Ranpeng. Amazing stuff, both of you. My question is for Ranpeng for now. So I could see how you had these really nice deflection for the plumes, right? And that was really clear and very interesting to see. But I was also wondering, sort of, obviously your phase transition is affecting your plume dynamics, but how is this then in turn affecting the slabs, right? So there has been work published before that's saying in a hotter sort of earth, your plumes are going to have a higher possibility of decapitating your slabs, and as a result, it's going to affect the sort of slab negative buoyancy and how that's kind of, affecting the plate tectonics at the surface, etc., etc. So I was wondering, there isn't a lot, like from your movies, I couldn't see like a lot of sort of like direct effects that are happening on the slabs, but I was wondering if you could maybe talk a little bit about that. Thank you.
Let me just reshare this slide. So it can definitely affect the slab. Yeah, and how much the effect is also depends on the collateral slope. And so just going back to. So can you still see my screen? No. Okay.
Yes.
Yeah, so I just want to go back to this phase diagram. And so we think the 660 transition can affect the slab, but as you can see on using this phase diagram, the 660, it doesn't really extend all the way to high temperature. So that's why in our hot models, we don't really see the effect of the 660 here. The slab would also be too cold for our OCI transition to like be in that transition range. So that's why like our study is focusing more on plume. And in our model, it's basically like a thermal, everything is a thermal structure, so we don't have different components, so we couldn't consider the effect from like those you mentioned, but those could be interesting factors to consider in the future study. And also I want to mention this phase or the current lookup table we are using are not from Lars and Carolina's most recent parallite table. So, and we heard from them that they could be a different Capron slope for 660 for their most recent property lookup table. So we are also thinking about to using the new table and see if the 660 could have more effect on stagnating the slab. Did I answer?
No, not quite. So I
Okay.
was aware that like I wasn't asking about the slab deflecting at 660. I was asking about the fact that you've got this plume that's deflecting at 660. Does that affect how the slab and the plumes interact with each other? Your plume is also hotter, right?
Oh, I see.
In an earlier mantle. So is there any way that this kind of thermal contrast between the slab and plume changes in the past, right? Because there has been work that suggested that like having a hotter plume would help to, for example, cut off your subducting slab, for example. And I was wondering if this deflection sort of would maybe help or not help or in any way affect the slab dynamics, not the phase transitions.
Okay. Oh, I see. Sorry, I misunderstood it.
That's okay.
Yeah, I don't have like any statistic to show, so I'm just answering from like memorizing the videos I see. I do see they can interact with each other, and especially if there's like a plume rising and if there's a slab going down, it can just totally impede the plume and basically just destroy it. Or also the opposite way, if a plume rise, it can also push the slab away. Yeah, I guess I just don't have a good answer to that because we didn't really focus on this with our current work. Yeah, sorry.
That's okay. That's okay. Thank you for answering.
All right, Daniel, it's time for a short question.
Cool. Actually, Ranpeng, could you open I had a question about that exact slide you had open. And great
Okay.
stuff, both of you, by the way. Really, really good stuff. It was just a question about, yeah, you were assuming some composition here, 82% Harzburgite, 18 basalt, which I'm sure is because this was sort of the best phase transition or phase diagram you had for thermal expansivity. But I was wondering, like, would it be a significant effect if this composition that you're assuming was different? Like if it was 30% basalt, 70 Harzburgite, or is that not even like reasonable? I'm just curious how this assumed composition influences maybe the results that you're seeing.
Oh, I see. So the one we are using, it's quite like commonly used pyrrolite compositions, and it's kind of like a model compositions for the silicate mantle. So maybe increasing to 30% would not be like very realistic. And if only changing the percentage for a little bit may not affect the property a lot. And yeah, but if we can maybe having different compositions, so maybe we can make some part like pure Harzburgite and some part pure basalt instead of like a mixing like this. We may see some differences, but that would require like improving the current method, because the current method in SPEC can only handle one compositions, and we are trying to make it to handle more than that. So we can maybe have purely basalt versus purely Harzburgite, and it will be interesting to see if they make any differences, but don't know it yet.
Sure. Yep. Cool. Thanks.
All right. Thanks again for both presentations and the answers. If you have any further questions, there is after the next sessions of short presentations at Pacific time, I think it's 12 to 13:30. There is some extra time. I'm not sure if they will be around, but otherwise you can send them an email for questions. With that, there will be a half an hour break now until European time 7 p.m. And after then, John Nadibov will take over as chair. So see you back then in half an hour.